I will start this video with a simple problem. Let's say that we have f of x equals to x cubed. Now, without actually sketching the whole thing manually, can you try to predict what will happen to the graph if we have this expression? Or can you try to predict what will happen to the graph if we have this expression? Now it's much more complicated, right? Now, how about this one? And how about this one? It gets more complicated each time. If you want to know the answer on how the graph will look like without sketching the whole thing manually, then you have come to the right video. Hello everyone, and welcome back to the maths. In this video, we are going to learn about transformation of function. If you haven't watched the previous videos regarding functions, I will put the link of the playlist on the top right of this video. Right, let's try to get into these types of transformation that we are going to discuss usually. The first type is going to be translation or shift, and it's divided into two types, the vertical translation or horizontal translation. We can actually imagine what the vertical translation will look like, and it's very simple. It's going to be up or it's going to be down. I mean down and up. And then for the horizontal translation, it's also easy. We can imagine that it goes to the right or it goes to the left. Pretty simple. But for the calculation, it's not so simple, especially for the horizontal translation. We will see later, okay? Now, let's go to the next type of transformation, which is reflection. This is by far the easiest type of reflection that you will learn. So there are two types. The first one, reflected by the y-axis. You can just imagine that the y-axis will act as a mirror. So if the y-axis acts as a mirror, you can imagine that the transform function is going to look like this. Pretty simple, right? And now for the second one, reflected by the x-axis, you can imagine that the x-axis acts as a mirror. So that means the transform function is going to be like this. We're going to see the calculation later on. Now, this type of transformation is actually one of the more complicated out of the three, I believe, yeah? So there are two types of stretch or compression. But before we discuss about each type, you can just imagine that you printed this function or this graph in an elastic paper or in an elastic rubber band, and then you try to stretch it either vertically or horizontally. So let's say we see the vertical stretch. So for the vertical stretch, which means you are going to pull it up and pull it down at the same time, which means it's going to look like this. So you try to stretch it. And if you try to imagine when you are stretching a rubber band, as you can see, the sides are going to shrink. But for the vertical part, it's going to be stretched. Okay? Now, it is also the same for the horizontal stretch. It is just that we are now focusing on the horizontal part. So again, let's imagine that we have a graph or a function printed on an elastic paper or an elastic rubber band, and then we try to stretch it horizontally. What will happen? So what will happen is this. So you try to stretch it to the left and the right at the same time, and as you can see, the vertical part now shrinks. But for the horizontal part, it expands. Okay, so we are going to see how the mathematics will be in this type of transformation. Right, the first one is going to be the vertical shift. If we try to shift this function, let's say upwards, it's going to be like this, right? Let's say we have two arbitrary points in the function, and then we shifted each of them by a points. If we try to imagine shifting each and every point of the function, we are going to get something like this. It's very easy to imagine, I believe. So now, if the original function is f of x, now the new function, the transform function, you can guess it, it's going to be fx plus a. So we can try to make a conclusion that fx plus a means that fx is shifted vertically by a units. And this one will be very logical. If a is a positive number, we're going to shift upwards. If a is a negative number, we're going to shift downwards. Let's try to see the examples. So over here, I have a straight line, y equals to 2x. And now, let's say I try to shift this 2 points upwards. Can you try to guess what the function will be? Yes, it's going to be 2x plus 2. So we just have to add 2 points out of the original function. And then, what will happen if I try to shift the red line 3 points downwards? Can you try to guess what the function will be? Yes, it's going to be 2x subtracted by 3. For the vertical shift, it's very simple. Now, for the horizontal shift, it's not so simple, as you will see in this slide. Let's say we have an original function, f of x, and let's say we have this point. This point is going to be our point of interest, which is 0, 0. And then, let's say we try to shift this function to the right by a units, which means the point of interest now is going to be a, 0. Now here comes the big question. Is the red function going to be fx minus a or fx plus a? Turns out this question is not so simple, unlike the vertical shift you saw before. So for this one, we need to know something. Yeah, it's going to be a bit complicated. We need to know this. As you can see in the original function in the green graph, we have a point 0, 0. So technically, we know that f0, because x is 0, f0 will be 0. Now, we need to remember something. This function actually has a characteristic of the original function, which is the green one. So the transform function, so the shifted function or the transform function has to be consistent with the original function, which means that the transform function will also need to have this. f0 equals to 0. It has to have that, okay? Now, let's assume that the red function is fx plus a, okay? So this one is going to be very logical, right? You move it to the right by a units, so it should be fx plus a, right? But as we will see, let's say that we input x equals to a because we want to get a, 0, right? So x is a, and then the value of the function is 0. And as you can see, we are going to have f2a equals to 0. Now, here is where this statement comes into play. As I said before, the shifted function has to be consistent with the original function. Now, the question is this consistent? Totally not. That's why it is a contradiction, and we know that if you shift to the right, turns out it's not x plus a. It's not x plus a, guys. So this one is wrong. It's a bit counterintuitive, yes, I know, but it is the truth. It is the fact. Now, let's say if we have x minus a, and then we try to input x equals to a, and then we say that the value of the function is equal to 0 to emulate the a, 0, just like what we did before. And over here, we got that f0 equals to 0. Now, is this consistent? Yes, it is. So it is consistent with the original function. So therefore, we have our conclusion. Turns out, if you move a function to the x positive direction, you're going to have x minus a. Not x plus a, but x minus a. Okay? So it's a bit of the opposite regarding compared to the vertical shift that we see before. Now, we can try to expand this concept. Let's say we try to shift the original function to the left, like this. Can you try to guess what the function will be now? Remember that if we go if we go to the x positive, we will have x minus a, but if we go to the direction of x negative, we will have x plus a. Okay, so it's a bit counterintuitive. It's going to be a bit of an opposite, yeah, compared to the vertical shift. So if we go to the right, minus. If we go to the left, positive. Right, now let's try to make a conclusion. If we have fx minus a, that means it's going to be shifted horizontally by a units. And remember, if it's minus, we go to the x positive direction. If we have a plus a, we go to the x negative direction. Remember that a should be a positive number, okay? And then, we also need to remember that whenever we do something with the x, it's always opposite of what we think it is. This sentence is going to be very useful when we are talking about the horizontal stretch, as we will see later on. Now, let's try to see some examples. Let's say I have y equals to x cubed. Now, can you try to guess the position of the function or the graph if we have this? Y equals to x minus 2 squared. Can you try to guess it? Right. So remember, it's a minus. If it's a minus, we go to x positive direction, which means we go to the right. So that means it's going to be over here. And now, let's see another example. How about this one, guys? X plus 3 cubed. Can you try to guess where it will be? Remember, x plus a, we go to x negative direction, which means it's going to be over there. So plus 3, which means we go 3 points to the left. Right, now let's try to talk about reflection. So if we want to reflect a graph by the x-axis, we can just imagine that the x-axis is the mirror. And let's just imagine that we have two arbitrary points in this graph, 0, y and x, y. And if we mirror it, what will we get in terms of the points? We will get 0, minus y, and then x, minus y. If we try to mirror every point in this function, we will get something like this. And then, as you can see, the original function is f of x, and the transform function is minus f of x. And this is logical because, as you can see, for every x value, you just mirror the y value. And when you mirror the y value, you get the you get the negative of it. You get the opposite of it. Okay? So that means minus f of x means that the f of x is reflected by the x-axis. So let's try to see an example. If we have 2x plus 2, the reflection by the x-axis is going to be like this. So minus 2x plus 2. Now the next one is going to be reflection by the y-axis. Again, we can imagine that the mirror is going to be our y-axis. And if we have an arbitrary point, we try to mirror it. We are going to have, can you try to guess what the point will be if we mirror it? It's going to be minus x, y. So every point will have the same x, y. It's just that the x value is going to be the opposite. So we will have this function, f minus x. This is the transform function. So that means f minus x means that f of x is reflected by the y-axis. An example will be something like this. So if we have x plus 5 cubed, we try to reflect it by the y-axis. So what will we get? Can you try to guess it? It's going to be y equals to negative x plus 5 cubed. I'm not joking. This is actually the real function. You can try to check it in Desmos, okay? Right, now let's try to go to vertical stretch, or usually we say a stretch parallel to the y-axis. That is the more formal language of it. And remember, if we try to stretch parallel to the y-axis, it's going to be like this, yeah? We have our elastic paper again, and then we try to stretch it like this. Now, let's try to see the original function and also the real function. The original function is the green one, and the red function is the transform one, okay? Now, let's say that the points in the original functions are x, y, and then the points in the transform function is going to be x, ky. So basically, when you try to stretch something or compress something, it's going to be at a factor or by a factor of k. So we are going to stretch or compress by a factor of k. So it means that every point is going to be multiplied by a factor of k. Pretty simple, the concept, yeah? And we can see that the x doesn't change, but only the y that's changed, right? So we can conclude that kfx means that f of x is stretched vertically or parallel to the y-axis by a factor of k. Now, we need to remember something about the k. If k is greater than 1, then we can just imagine, logically, that it's going to be a stretch. You will stretch the function. But if you have a k between 0 and 1, you can also imagine that you are compressing the function, right? You are compressing the function so that it shrinks. Now, a bit of a question, guys. What about if we have a negative k value? Can you try to guess what will happen? If we have a negative k value, we are going to reflect it. Remember from the reflection slide that if the k is negative, we reflect it. Okay, we reflect it by the x-axis. So we reflect it by the x-axis, and then we apply this stretch or compression value. Okay, so it's going to be double. You reflect it and then you stretch it. That's what happens if you have a negative k value. Let's try to see the example, shall we? So the first example is going to be y equals to x cubed. Now, can you try to imagine if we have 2x cubed, is it going to be stretched or compressed? It's going to be stretched. You're going to pull it upwards and downwards at the same time. But how about if you have this, 1 over 3x cubed? You're going to compress it. So it's going to be a bit more flat, just like this. Right, let's go to the horizontal stretch. Let's try to imagine again what will the horizontal stretch will be, or parallel to the x-axis. Yeah, that's the formal language. If we try to stretch it horizontally, it's going to be from here to here. But in this case, I will try to use compression as our first definition of horizontal stretch, yeah? Because as you can remember, that if we try to do something with the x, it's going to be the opposite, okay? So now you will be able to imagine why I try to give you an illustration of compression rather than stretch. Right, let's try to see the comparison between the original function and the transform function, like this. And let's say that the points in the original functions are going to be x comma y, and if we try to compress it, the points are going to be kx comma y. Okay, so we try to compress it, and the points are going to be kx comma y. For the same y value, we have a different k value. So a positive k value, technically a k greater than 1, will try to compress the function. Again, remember, whenever we do something with the x, it's always opposite of what we think it is. Remember that in the vertical stretch, k positive means stretch, now it means compression. Okay, remember that. So we have fkx means that f of x is compressed horizontally by a factor of k. So if k is greater than 1, just like what I said before, it's going to be compression. And if k is between 0 and 1, it's going to be a stretch. What about k negative? Same as before, yeah? So you try to reflect it, and then you try to stretch or compress it. Let's try to see an example. Let's say I have x squared minus 2. Now, can you try to imagine what will happen if I have this function? Yes, because the k value is a positive number greater than 1, we are going to compress it, as you can see over here. And how about if we have this? We know that the k value is between 0 and 1, so we are going to stretch it. So that's the difference. Remember the difference, yeah? If we do something with the x, it's always the opposite of what we think it is. This is usually how I memorize it. And I hope it can be useful to you guys also. Right, guys, let's try to recap what we have known so far. So first, f of x plus a means that it is shifted upwards by a unit. If x minus a, it is shifted rightwards. Okay, so to the right means x minus a, and to the left means x plus a, just like what we learned before. So this is the translation transformation. And then, how about for the reflection? Yes, this one, yeah? Minus fx means it is reflected by the x-axis. F minus x means it's reflected by the y-axis. And then for the stretch or compression, it's going to be like this. Kfx means that fx is stretched vertically or parallel to the y-axis by a factor of k. And then fkx means that f of x is compressed horizontally or parallel to the x-axis by a factor of k. So those are the transformations that you are going to learn usually in school. Right, now let's try to see some examples in the case where we combine the transformations. So we have a x cubed, f of x equals to x cubed, And we need to find the image or the transform function after in this specific order. Yeah. First, vertical translation of 5 units to the y positive. Second, horizontal translation 2 units to the x positive. Third, vertical stretch by a factor of 3. Let's try to see one by one, shall we? So we have ourselves an original function, our original function, and then we have a vertical translation, just as what is written in the problem, 5 units to the y positive. Now, first, can you try to guess what the function will be? Remember, it's a vertical translation. It's going to be x cubed plus 5. So that's the first one, okay? Now the next one, horizontal translation. And as we can see, 2 units to the x positive. Can you try to guess what will happen? It's going to be x minus 2 cubed plus 5. So I'll try to put this down here just for clarity. The next step or the last step is vertical stretch. So we're going to stretch the function vertically by a factor of 3. Can you try to guess what will happen? It's going to be like this. So you multiply the whole thing by the factor of 3. If you try to change the order, the resulting function might be different. You can try it out yourself, okay? Right. So I want to give you an example of the graph for each step so that you can try to visualize it. So for x cubed, it's going to be like this. And then for x cubed plus 5, remember, it's a vertical translation. So that means you just have to shift it up. So it's going to be like this. So you shift it up by 5 points from the purple graph to the green graph. Now, if we want to obtain this, remember that it's going to be a horizontal translation, especially 2 units to the x positive. So the graph will look like this, guys. And as you can see, the new function or the new graph is the blue one, and I also give you the green one just for comparison. As you can see, it is shifted 2 units to the right. And now the last one is when we try to scale it, when we try to stretch it vertically. So it's going to be like this. The blue function is the one before, this one. And the orange function, as you can see over here, is the new function where we stretch it vertically. Okay, so as you can see, it's a bit stretched upwards. So the orange graph is actually the transform function after all those steps. Now, let's try to see the next question. We need to determine the sequence of transformation from y equals to square root of x to this transform function. Now, if we want to determine the sequence of transformation, we need to prioritize something. So we cannot just try to guess the transformation. We cannot just try to ignore the order. So the order actually matters. And now, how can we find the order? There is a rule, guys. So now, let's try to compare first. If you have a vertical transformation and a horizontal transformation and a vertical transformation, which one do you think is more prioritized? The answer, horizontal. Horizontal transformation will be prioritized when you are determining the order of transformation. And the next one, you have a stretch and translation. Which one do you prioritize? For this one, let's see a simple analogy. If you pay attention to the previous materials before, or you can try to go back to the stretch or translation material, stretch is we usually relate this to a multiplication or division by a factor of k, and for translation, we usually connect it with plus or minus a units, right? Now, in simple mathematics, which one is prioritized? Multiply division or addition subtraction? The answer is very obvious. This one. So, whenever we are determining the sequence of transformation, we need to prioritize the horizontal transformation, and specifically, we need to prioritize the stretch or scaling transformation. After that, we can go to horizontal translation, and then we can go to vertical stretch, and then the last one, vertical translation. Okay, so that's the priority. horizontal stretch, horizontal translation, vertical stretch, vertical translation. Let's try to see the problem. So first, we should determine what is the horizontal stretch in this case. Can you try to guess it, guys? And as you can see, we have a factor of 2 over here, right? So the first one, horizontal compression by a factor of 2. And now the next one, horizontal translation. Can you try to guess what the translation will be? It will come from this positive 1. So if it's a positive 1, that means we translate it 1 unit to the x negative. Okay? Now the next one, vertical stretch. By what factor do we stretch this vertically? By a factor of 3. Vertical stretch by a factor of 3. And the last one, vertical translation. By how much we translate this vertically? We use this number, plus 4. So vertical translation, 4 units to the y positive. If you don't believe me, you can try to work on these steps by yourself, and eventually you will gain yourself this specific function. Okay? So this is actually the rule to determining the sequence of transformation. Right, now it's exercise time. So I've prepared 2 numbers for you guys to do it so that you can do it yourself. And you can leave the answer in the comments if you want, yeah? But if you want to check the answer key, I'll leave it in the description box, okay? Right, so that's it for this video. In this video, we learned about transformation of functions. What do you think about this video? Please leave a comment and don't forget to leave a like and don't forget to subscribe. I'll see you on the next video. Thank you.